The statement with sodium hydroxide is a reactant with vinegar, bubbles form. That's just an observation. I'm observing that that happens. I might come up with educated guesses as to why it's happened. I might do experimentation to figure out why it's happening. But all I know from reading this is I've observed it happening. So that's an observation. Now remember, with significant figures, with our zeros, if there is a whole number before the decimal and another number, then those are significant. But here we don't. These are just placeholders. So our first significant figure starts at 7. So that is, of course, 5 significant figures. Know your significant figures. What's significant? To be more clear, I might write this in scientific notation. But make sure you know your significant figures. Number 3 was really the best answer was blood. But then you could spin blood down and separate it. But it does appear to be all homogeneous until you do that. It is a mixture though. The big thing is it's not a pure substance. Blood is not an element or a pure sample of a compound. It is definitely a mixture of different things. So a more clear homogeneous mixture would be a saltwater solution. Something like that where you clearly can't tell the difference. So blood's kind of ambiguous, so I gave everyone a point there. Clearly chunky peanut butter, you could clearly see the whole peanuts and the non. And of course there's sugar and other stuff in there. Ice water, you can, technically that's a pure substance, assuming it's DI water. If it's ice tap water, then it is a mixture. But the fact that there's ice in liquid, that's just 2 different states of it. Salad dressing, again, that's a little ambiguous. I guess there's some salad dressings that don't have flecks of seasoning and stuff in it, but most of them do. You can usually see the differences. Italian dressing separates into 2 separate, because we have oil and water, and they don't mix. But like a creamy dressing, you can usually see the specks of different things. So like I said, this was a bit more ambiguous than I wanted it to. Salsa typically has chunks of things. All of those would be heterogeneous. But I gave everyone a point because it was a bit more ambiguous. I'll try not to have one like that on the exam. I'm sorry about that. As far as a chemical change, sugar dissolving in water, that's a physical change. No chemical reaction is occurring. Sugar is still sugar. It's just interacting with water to go from a solid to a solution. Ethanol evaporates at 79 degrees Celsius. Again, that's just a change in physical state, so that would be a physical change. Sublimation is going from a solid to a gas. Again, that's just a state change, so that's a physical change. But when you mix vinegar and baking soda, that's a chemical reaction. That's where the bubbles come from. So that's a chemical change. Other examples, rusting of iron, things like that. Those are all chemical changes. Here, if we look at the list of what the student has, the numbers, first off, are nowhere near each other. 4.11, 4.81, 4.95, 3.75. So there's really no precision there. As far as accuracy, the actual amount should be 4.75 grams of sugar per milliliter solution. And as you can see, we're jumping pretty far from that. So really, she's not precise or accurate. Though I did get some points towards B. But remember, we have 2 numbers after the decimal point, which means this is a known and this is ambiguous. So if she was accurate, then we might have 4.71, 4.72, 4.75. That would be accurate because 7 is known. So it depends on how many decimal places you actually have with your known value when you're comparing accuracy. So this one's not accurate because if it was, then this value would be correct. This last ambiguous value might jump, but if we only had 2 decimal places, 4.7, and these were all close to 4, that would be more accurate. But because we have the 2 decimal places, that means that our instrument was sensitive enough to go all the way to that second decimal place. But I did get partial credit for B, because you still did get that it wasn't precise. But it's not precise or accurate, so it should have been C. If we're looking at this one, this is a case where do not round until you're done. And I think that's why a lot of people got this one a little bit wrong. So the answer should be D. So let's look at that. We are going to do our addition first, is in parentheses. So our 249, and we have the same numbers, so you really didn't need a calculator there. Plus our 41 is going to give us 290.362. Now remember, when we're adding, we're going with the least amount of decimal places. So in this case, we should have 0 decimal places. I know this is a 0, but at this point it's still significant, because this 1 is significant. So if you try to round too soon, you might try to drop the 0. But we can't drop that 0 because it's so significant at this time.
I have a question.
Yeah?
I thought when adding you had to use
The lowest number of decimal places. No, lowest. We can only be as remember, what we're doing is, with significant figures, is trying to figure out how accurate we are. If I'm measuring two values, and I have an instrument that measures all the way here, and I have an instrument that only measures to no decimal places, I can't add these, I don't know anymore. Because my second measurement is not that precise. I can only be as precise as my least precise measurement when I'm adding or multiplying. It's the least number of decimal places. I can only be as precise as my least precise instrument. My least precise instrument is this, 0 decimal places.
Wouldn't it be 2 decimal places for the answer?
Yeah, wouldn't it be 260 for answer?
It's 0 decimal. There's 0 decimal places, so this is 0 decimal places. That's 3 significant figures, but 0 decimal places. These are what I'm still following. That's no significant figure, no decimal places. These are still significant. If I had a higher measurement than 41, I'd still have precision at this point. I don't have precision here, to the lower end. I have a smaller number, but I still would have precision here. It's all about your instrument. We're trying to figure out, if we have an instrument, how precise can we be based on what we have to measure with. So if I were rounding here, my answer would have these 3 numbers, and they would all be significant, whether the fact that's a 0 or not. So what I'd want to do is write it in scientific notation, so it wouldn't be, that 0 wouldn't be ambiguous. So don't let the fact that 0 is there confuse you. It's not. But what I do know is that 362, I don't really know, because I'm adding one thing that's very precise all the way to the hundreds, and one thing that's not. Then, now I'm going to multiply. So this is 0 decimals, but it is 3 significant figures. And I'm multiplying that by something that has 5 significant figures. So my overall is going to have the least amount of significant figures, which is 3. Because we go by the least number of significant figures in our final. And it's always the least. Least decimal places or least number. Because again, we can only be as clear as our less sensitive instrument that we're using. So that's why we do these significance. And it will make a lot more sense when you get in the lab and you start working with instruments and you see the difference between how clear you could be with this size ruler versus another size ruler, or this instrument or that instrument. But basically, let's say I'm measuring 2 different things. I'm measuring an apple on one of those scales in the grocery store that has little tick marks, and it only goes to 1 decimal place. And then I take another apple and I measure it on a balance in the lab that goes to 4 decimal places. And I want to add them together to get my total number. I'm only going to be able to report my least accurate based on the apple I measured in the grocery store. Then if I had a really sensitive instrument, I would see that reported from my actual mass. Because the one I measured in the grocery store, I don't know those extra decimal places. How can you prevent that? Well, if you're doing something like mass, try to measure them in the same thing. But sometimes that's not an option. If I'm talking about 2 apples, it would be silly of me to try to measure and add together a mass from 2 different instruments. But sometimes you might be measuring something in the microliter scale and something else in the liter scale, and you're trying to add together to get the total amount. So you do have to consider those values. So it will make more sense when you're applying it with instruments and you start seeing the difference in lab. So I gave partial credit for A. And most people only counted these 2 as significant and dropped that 0, I think. But don't drop it until the end. The fact that it's a 0, if it would have been a 1, it wouldn't have made a difference with our amount. So this one's a little bit of math. We're determining the volume of an object that has a mass, a certain mass, and we have a density. Y'all have a good day. So we want to know volume. Question mark. So we know our mass. And we don't really know what the object is, but we do have the density of the object. And our density is 19.3 grams per centimeter cube. So we need a couple of relationships here. Kilograms and grams don't cancel out. And clearly our volume is going to be in milliliters. And I know that because that's my answers. They're all in milliliters, so I must be converting them to milliliters. So we need some relationships. Density is one of our relationships. That's a given relationship that is specific for that object. So what that tells me is for every 19.3 grams of that object, I have 1 centimeter cube in volume of that object. But I need a little bit more. 1, my mass is in kilograms, and grams and kilograms don't cancel out. So I need that relationship. Remember, kilograms is much bigger than grams. So 1 kilogram is equal to 1,000 grams. You do need to know these. Don't get this one mixed up. A common mistake I see is 1,000 kilograms equals to 1 gram. Now remember, kilograms are big. They're a big measurement. And then our other one, and I wanted to see this because later on it's going to make a difference, even though it doesn't numerically make a difference to your final answer. And that is that we know 1 milliliter is equal to 1 centimeter cubed exactly. So I do want to see that right now, because even though it doesn't actually change your number, later on we'll see these kinds of transformations really important. So we want to follow our units. It'll help you not make mistakes later on. So we can set that up. We can take our kilograms, and we have a way to convert that to grams. Then our density allows us to convert our grams to volume, which is centimeters cubed. And then we can figure out our milliliters from there. I'm starting with my known mass. That's not a 0. Sorry. And now I can use my conversion. My kilograms are at the bottom, so they cancel out. And my grams are at the top. Now I can use my density. My grams are going to be at the bottom. My centimeters cubed at the top. Of course, we want our volume in milliliters, so my centimeters cubed and 1 milliliter. Again, that last step is really so I don't lose my units. So when I do that calculation, I get 23.6062. And I started with 3 significant figures. Remember, density is a measurement. And I have 1, 2, 3, 4 significant figures there. 3 is less, so my answer should be in 3 significant figures, which is C. Though if you showed the work, I gave a good bit of partial credit for B, if the work was there. I did have a question. Why isn't the 1 and 1 centimeters cubed equal 19.3 grams? It's because this is normalized. So the 1 has infinite significant figures. Meaning when it was measured, you might have had measured, okay, for 50 grams, I have 1,500 milliliters. But you're going to normalize that. So something is at 1, just to make it easier, typically. So that's why it's infinite. But it is a measurement, so we do have to consider it. Now, 1 millimeter equals 1 centimeter squared. That's also infinite. And this last one, we're also looking at just a word problem. Here we have gas, and we're told the price. Now, this is giving us a relationship. This tells me that for every liter, whatever that is, I put in my car, I'm going to pay $1.399. That's my relationship. That's specific for that gas station in that place in Canada. So if I want to know how much it'll cost to fill up my car, if I know my car is 12 gallons, I can do that conversion. So my volume is 12 gallons. I'm just going to put gal. I have one relationship that is 1.399 gallons. I'm tired, sorry. Dollars. And I'm just going to write dollars, but you could have just left a dollar sign. Equals 1 liter. Of course, I don't have a relationship between liters and gallons, so that's something I'm going to need. This is not one you need to memorize. You can, in fact, look this one up. So if I look down, I see that I do, in fact, have a relationship between gallons and liters. So I'm going to use it. So that's my other relationship. And again, I will give you this. You do not need to memorize those. So now I have a relationship between gallons and liters, and I have a relationship between liters and dollars. So I can convert my gallons to liters, and then I can convert that to my dollars. So I'm starting with my 12 gallons. I want my gallon at the bottom so it cancels out. And my relationship between gallon and liters is the one that I looked at. If I figured whatever that was out, I'd have my liters. So now I can use my relationship given to me here. 1 liter equals to $1.399. One 2.00, that's 4 significant figures. Of course, my dollars is in 4 significant figures as well. So I'm going to report this in 4 significant figures. So it's $63.53. Oops, $54. Any questions with that quiz that I didn't touch on? So now we're going to have a couple in later quizzes where we're applying these concepts of the formulas. I'm sorry when I upload these, for some reason when it saves it, it looks all fuzzy. I don't know why it does that. Okay, let's start with quiz 2. So I changed this because I had to give a review for some people that had missed. Also, any of my soccer girls are in here that had to take this at a separate time, your quiz is a slightly different from the one I'm going over because you had a different set. Anyway, when I changed it, I didn't realize that 2 of the answers agreed with the law of definite proportions. So actually, both C and E are correct with the law of definite proportions. That says that if we have 2 different samples of a pure substance, each sample is going to have the same ratio of atoms in it. So for example, C, 2 different samples of table salt are fine to have the same ratio of sodium to chloride. That's true. We always have 1 sodium ion to 1 chloride ion. Doesn't matter where you're getting table salt from. If it's made up of pure table salt, that's going to be true. Let's not get into the ones that have some potassium in it. Let's pretend like it doesn't. Some table salt does have potassium. Let's just pretend like it doesn't. And E, nitrogen dioxide, which you should know how to draw now, NO2, nitrogen dioxide, always has a mass ratio of 2.28 grams oxygen to 1 gram nitrogen. That's true, because we always have 2 oxygens to 1 nitrogen. So E and C were correct. B, however, is the law of multiple proportions. If we have 2 different compounds formed from carbon and oxygen, meaning we could have CO and CO2, then if we keep carbon constant, we can compare oxygen and oxygen in each one, because basically the reason why is oxygen has specific bonding patterns and carbon has specific bonding patterns. And as far as a sample A containing chlorine is found to have 3 times as much Cl35 as Cl37, that has to do with our isotopic abundance. That's not really one of our laws. So C and E were both correct. I gave equal credit, and I'm sorry if you were staring at that for too long on the quiz. Because the other quiz I had was asking about the law of multiple proportions. And then I changed it for this one, and I didn't realize that I had 2 answers that worked. But they're both equally right. Here, which element? We don't need to know anything but the amount of protons. That's all I need, P. Protons is 26, so if I look at the periodic table, that's iron. Don't get confused. Our protons is not our mass. Our protons are our atomic number. That's the biggest confusion. So iron has an atomic number of 26. Remember, our mass is going to be our neutrons plus our protons. And our charge is going to be the difference between our protons and our electrons. So we know a couple of things about this particular element, but I was only asking for which element it was. In 3, we don't know what this element is because there's no X. Well, we do because we know its atomic number. So here what we're showing is the atomic number at the bottom, and at the top is going to be our mass. So our answer for that one, of course, is not D or E, because our atomic number equals our number of protons. And we know our number of electrons equals our number of protons, because if we had a charge, it would be shown here, just like a normal charge is. We don't have a charge shown, so we know we have equal protons and electrons, which is true for B. That's the only one that is true for, but let's also make sure that our neutrons are correct. Remember, our mass is our protons plus our neutrons equals our mass. So 40 minus 18 should equal to 22 if B is right, and it does. So B is correct for protons, neutrons, and electrons. Any questions with that? Remember, you cannot have more protons than mass. So if you get confused about which number is the mass, it's the bigger one. Here, the number of electrons for carbon-13 doesn't matter. Doesn't matter that it's the isotope carbon-13. All that matters is we know its charge and we know its carbon. If I ask you what's the number of electrons for carbon-12 with a -2 charge, it's the same answer. The fact that it's carbon-12 or carbon-13 only affects the number of neutrons, but not the number of electrons. So we know carbon, we know its atomic number, and so we can figure out how many protons it has. And if we look at the periodic table, carbon is 6, so we know it has 6 protons. Its mass is 13, but we know it has 6 protons. And we know that because it's carbon, so we can look up its atomic number. If it has a -2 charge, that means it has how many? Do we have more or less electrons than protons? More. And we have 2 more because it has a 2 minus. So our number is 8. Remember, electrons are negatively charged. So 6 plus 8 minus is going to give us a 2 minus. So all we really needed to know was the charge and the fact that it was carbon. The fact that it's carbon-13 makes no difference, at least for the electrons. Here, which of the following pairs are most similar? Let's look at our periodic table. Oops, that's not a D. That's not a Y. I can't type on this one. So, our elements that are in the same column are most alike. And if we look at our choices, nitrogen and nickel, here's nitrogen, very different. One's a non-metal, one's a metal, that's clearly not the answer. Then molybdenum and tin. Tin is right here. MO is somewhere over here. There it is. It's not the same. Pretty clear. Sodium and magnesium. Now they're close to each other in the periodic table, but they're not in the same column. They do have relationships, what we'll learn about in chapter 7 and 8. They're similar in size, for example, but they behave pretty differently, and they're in a different column. So those are not the answer, though I didn't give any partial credit for this one. Same with chlorine and sulfur, very different compounds. But if we compare silica and carbon, silica is right under carbon on the periodic table. They're going to be pretty similar. So that's our answer. The ones in the same row are usually pretty similar. And we're going to learn why in more detail later on. I wish this book went into that earlier, but it doesn't, and I have to follow it because of people in 113 labs. So we're going to learn why. It's just going to be later in the semester. Here, which one has the fewest moles? Well, they all start out with 4 grams. So we're starting with the same amount. And we can look at our grams per mole of the periodic table. So that means we're going to have our grams at the bottom. So the larger our mass, the smaller that number is going to be because we're dividing by it. You can actually calculate all of them, and what you will see is that rubidium, who has the highest atomic mass at 85.47, is going to have the smallest number of moles after, because that's the biggest number and we're dividing. We're starting out with 4 for all of them, so they're comparable. And you can go in and you can calculate the number of moles for each of them, and you would see that C would give you the lowest number, but you didn't have to, unless if I specifically asked you that number.
Look on your table and find the mass of the RE.
Nope, the mass goes on the bottom. Look, for it to cancel out, our grams need to go on the bottom. Our mass on the periodic table, this is what we're starting with. We're converting this using a relationship. We start with what we're converting. We use our relationships to convert them. So this is 4 grams X, whatever X is. Which I'll do this one next because it's more related, and I'll do 7 last. So this one's actually the calculating. We want to know the mass of lead. We're given the atoms of lead. We want to know mass. And I gave you this just for times constraints, but you could look up on the periodic table for the atomic mass of lead. And the atomic mass of lead is 207.2 grams per mole. That's my relationship between grams of lead and moles of lead. So what this tells me is for every 207.2 grams of lead, I have 1 mole of lead. That's my relationship. So I need to take my atoms of lead and convert that to moles of lead. Can I do that with this relationship? Directly. Not directly. I need to do something first. Because atoms isn't going to be canceled out by grams or moles. So I need a relationship between atoms and either grams or moles. Our relationship is between atoms and moles. Or moles and whatever things we're talking about. And recall our dozen of eggs. A dozen eggs always equals 12 eggs. A dozen elephants always equals 12 elephants. So that's our relationship. 1 mole always equals to 6.022 times 10 to the 23 atoms. You must know this number, and you need to know the relationship that it tells us. And that's our relationship. Just like 1 dozen equals 12 things, 1 mole equals 6.022 times 10 to the 23rd things. This thing could be atoms. This thing could be molecules, like it was today on the quiz. This thing could be footballs. This thing could be feet. I don't know. I don't care. It's things. So know that relationship. So now we can convert our atoms lead to, we have a relationship between atoms and moles. Our moles lead. And I usually don't put the E, but because it's common not to put the E, where the whole thing is MOLES. I don't know why we just drop the E, but it's pretty common that that happens. And then we can figure out our mass in grams lead. Now I could take this further and ask you for kilograms or milligrams, which you should be able to do once you get to grams. But in this case, we're stopping at grams. So we're starting with our 1.9 times 10 to the 24 atoms of lead. And we're going to use our conversion to convert that to moles. And our conversion is our Avogadro number. We want our atoms on the bottom. And that's our 1 mole of lead at the top. Atoms cancel out with atoms, so we're good. So now we have our mole of lead. Now we want to convert that to our grams. We have that relationship from our periodic table. So 1 mole of lead, that'll cancel out, is related to 207.2 grams of lead. I'm left with grams of lead. That's what I want, so I'm done. Now all I have to do is the calculation. I started with 2 significant figures. My periodic table molar mass is in 4. Avogadro's number, I have 4. So my final answer is going to be in 2 significant figures because that's what I'm starting with. So that comes out to 653.736. But because I only want to show 2 significant figures, so I'm not ambiguous, I'll just move it to scientific notation, 6.5 times 10 to the 2, because it's more clear that way than just putting 650, because that 0 at the end can be a little ambiguous. 650 is not necessarily wrong, it's just this way is a bit more clear. So that's B. Does anyone have any questions with setting these up? It's just like what we did on quiz 1, except now we're using other relationships that you learned from the periodic table and that you need to know with Avogadro's number. Okay, here we're looking at our average atomic mass unit. Now remember, there's a formula for this. You don't really need to memorize it. It's just a weighted average. If you were trying to calculate your grade, maybe, and if you're having trouble calculating grades, that's an issue. If you were trying to calculate your grade, and quizzes are worth 20%, tests are worth 40%, tests are worth more. That's a bigger weighted average. So that's all this is. So what you're given is, you have gallium, and you're given its atomic mass. This is the atomic mass for all isotopes. It's our average atomic mass. So I'm going to put, remember in math, the line on top means average. I'm just going to put atomic mass with the line on top. That's our 69.723. I got to assume from this particular question and the way it's worded that we only have 2 isotopes. So we have 2 isotopes of gallium, gallium-69, and the other isotope, we don't know what the mass is. So we're trying to figure that out. Now we are given our atomic mass of gallium-69, which is in a lot of significant figures, but 68.926. So this is my atomic mass of, I'm just going to put 69 at the bottom. And I know the percent that I have of that gallium. So that's my fractional abundance in percent of 69. I don't want to use the percent, I want to use my fractional abundance. So I'm going to convert that from percent to my fractional abundance. So I'm just going to do that by either dividing it by 100 or moving my decimal place. So now I have one of my isotopes. My second isotope, gallium, I don't know. I don't know what my atomic mass is. I'm going to call it X. So that equals to X AMU. Now my fractional abundance I can figure out. Assuming I only have 2 isotopes, if I have 60.11% of one, I can calculate how much I have of the other, because remember, percent equals 100. So my percent of X is just going to be equal to 100 minus 60.11, and that gives me 39.89. Now again, that's percent, so that tells me my fractional abundance of X is 0.3989. So plugging that in, I know my fractional abundance, my average atomic mass is equal to the sum of the atomic mass of one isotope times the fractional abundance of that isotope. So I have 2. So I'm going to set this up. My average atomic mass is just 69.723 AMU is equal to my atomic mass of my isotope 69 times my fractional abundance, which was given, plus my fractional abundance of my unknown, which I'm going to call X. I'm just going to not show the AMU. Times my fractional abundance, which I was able to calculate. So now I just have one unknown. I just have to solve for X. Now because we have all these decimal places, don't round till the end, because otherwise you'll get a number that's off. So if I multiply 68.926 times 0.6011, I get 41.4341 plus 0.393 I don't know. Me trying to go ahead of myself while I'm writing numbers down. 3, 9, 8, 9. And I'm just going to put my X here. Because that's the way I like looking at algebra problems. Now I have AMU in blue on both sides, so I can just subtract AMU from AMU. And that's going to be equal to my 0.3. Oh, I'm so sorry, guys. That clearly doesn't equal that. 20.2915014. I'm keeping all those things. Yeah, it is 28. I'm sorry. So I can divide both sides by my 3989, and that will give me my mass of my unknown isotope. I think the biggest issue that most students had was not recognizing that this gallium has an atomic mass of 69.723. That's your average atomic mass. That's all of gallium. And I think a lot of people missed that. So make sure you're reading your problem so you can follow what's being given to you. Any questions with quiz 2? Okay, let's move on to the quiz from today. Now I'm going to upload these keys that I'm writing in, so you don't have to feel like you have to completely write down all the words to these. And again, I'm going to upload this, what I'm talking right now to Moodle. So, what we're looking at here is we have 3, our first question. We want to know the empirical formula. Remember, our 803 is a polyatomic ion, and we have 2 of those total ions. So you're never changing anything about the ratio to nitrogen to oxygen. Because if you do, then that's not the same polyatomic ion. So don't ever touch that. But what we know is we have 2 of them, and we have 2 mercuries. So our empirical formula is the lowest ratio whole number. We do have a number that we can divide 2 and 2 by and get a lower number. And that's, of course, 2. So if we divide it by 2, we get mercury NO3. That's 8. And again, you can't break up your covalent bonds with your polyatomic ion. So this would be our empirical formula. Okay, here, which is not a molecular compound, H2O, that's covalent bonding. That's all non-metals. CH3Cl, all non-metals, covalent bonding. NH4, NO2. You should recognize, oh, sorry, I skipped an H3. NH3, no charge, also just covalent bonding. But NH4, NO2, you should recognize that. One reason, because it's the exact example I gave in the lecture notes. But 2, you should recognize your polyatomic ions. And, unlike I won't be giving this on the test on Monday, I gave them to you today. And you clearly see we do in fact have these 2 polyatomic ions, our ammonium and our nitrite. So even though we do have covalent bonding in it, it's not an overall molecular compound, it's an ionic compound because we have that ionic bond. So it's not a true molecular compound, even though we do have some covalent bonding. Our molecular compound is only our covalent bonds. And then PO2 is also all nonmetals, no ions. The only positively charged polyatomic ion you are required to know at this point is NH4+. So always watch out for that. Now NH3 is not the same as NH4+. Just like sodium in the elemental form and sodium ion is not the same. So don't make the mistake of putting NH3 as the same thing. There's a different amount of hydrogens, which means NH4 has a positive one charge, NH3 doesn't. And when you get to organic chemistry, you're really going to look into that. We talk about it a little bit in chapter 8. Here we're looking at the name. First off, you should recognize we have a polyatomic ion, and that polyatomic ion is the carbonate ion. And again, I gave it to you for this particular quiz, but I won't always. But if you look up the carbonate ion, it's CO3 2-. So you need to know that. So I don't know what is the charge of titanium because it's variable. It's a transition metal. So I have to figure it out. I know I only have one titanium and I only have one carbonate. So for them to cancel out, they have to equal to 0. So just to be thorough, I only have one titanium, that tells me that from the formula. Plus, I only have one CO3 polyatomic ion, that tells me that from the formula. I know I'm being really thorough right now. It's going to equal to 0. So that means X plus 2- equal to 0. So X must equal to 2+. So that has to be specified in the name, titanium 2 carbonate. I did give partial credit for titanium 3 carbonate, but we only have 1-to-1. And I know that because the formula, I have the empirical formula. And if this isn't in parentheses, we only have one ion of that polyatomic ion. If we have multiple, we have to put it in parentheses, like is shown up here. I'm short. A covalent bond is a sharing of electrons, D. Typically between nonmetals and nonmetals. So B is an ionic bond, a bond between a metal and a nonmetal. Covalent bonds is between nonmetals. Between two polyatomic ions, that is a ionic bond. The transfer of electrons is describing an ionic bond. Transfer electrons and you have a charge. A bond between a metal and a polyatomic ion is also describing an ionic bond. Here, okay, so first off, we have a hydrate because we have this H2O. We have to specify that we have a hydrate. So we use that by putting hydrate at the end. So clearly B isn't correct. Now cobalt is a variable metal, so we don't know its charge, we have to figure it out. Now chlorine is not a polyatomic ion, we have 2 of them. What is it? How do we figure out the charge of chlorine? We look at the periodic table, where it is. Since 6, 8 minus 6 is going to be, since 7. So it's going to be -1. 7 minus 8 gives us -1. Why 8? Again, we're going to learn that in chapter 7. It really annoys me we don't learn that till chapter 7. But there is a reason why we use the number 8. It has to do with the noble gases. So we'll get to that later. So again, we have to balance this charge. We don't know what cobalt is. The amount of hydrogens we have, H2Os, I'm not even thinking about that right now. So we have 1 cobalt plus 2. Why do I keep on wanting to write 2? Chlorines with a -1 charge, and that has to equal to 0. So our X for cobalt must be equal to 2+. So cobalt 2 chloride, which we see in both A and C. So the difference between A and C is our hydrates. We have 6 waters, so we have to show that with our prefix. 6 is going to be hexa, so it's going to be A. And again, you can remember the difference between 6 and 7. 7 is hepta. 6 has an X in it, hexa has an X in it. So a good little trick to remembering that one. Most of the other prefixes are pretty straightforward. You already know mono, di, tri, tetra. I mean, everyone in here has to have done geometry at some point. And we use those prefixes a lot for everyday things. Like we know octopus has 8 legs, things like that. So you can remember most of them, but hexa and hepta students always get mixed up. All right, so here we have a covalent bond between 2 nonmetals. We have carbon and we have sulfur. So we're still going to have carbon and sulfide. We always change the N to IDE for this one. But we need to specify how many carbons and how many sulfurs. We do not do this with the same way we do with our metals. We do this using our prefixes. So we have 1 carbon, that's monocarbon, and we have 2 sulfides, that's disulfide. But we never use the mono for the first atom. Why? I don't know. But that's the rule. We never use mono for the first atom. So the correct answer is E, carbon disulfide. I did give partial credit for B, monocarbon disulfide, but we always drop the mono if it's on the first atom. On the second atom, like dihydrogen monoxide, we keep it, but not on the first atom. And remember, we always put the more metallic atom first. So carbon is closer to the metals than sulfur is. So it's drawn first. Any questions with that one? And A is wrong. We need to specify how many sulfurs. Carbon can bond to sulfur multiple ways, so we need to specify which way it's bonding. 7, this is an acid. So we have to specify that. This is an acid with our polyatomic ion, so we will not be using hydrogen first. We only use hydrogen for our diacids. And remember, for these 8, we're going to change to ik, and ite to us. So the question is, we have NO3. It's NO3 1 minus because H is always +1. So the question is, what polyatomic ion is that? And it's nitrate. So 8 is going to change to ik. So our answer is D. I gave partial credit for 8. Remember your 8 and ik and your itiness. You have to memorize it. I don't like to give you much things to memorize. This is one you have to memorize. Sometimes for naming, you're going to have to memorize stuff.
For the hydro, which ones do for the hydro?
The binary acids. The acids that just have 2 different elements. Things like HCl, HBr. So things that only have 2 different types of elements. If you have a polyatomic ion, you don't put the hydro. And the only math I gave you on this quiz, well, except for really simple math, we want to know how many molecules, not moles, molecules, we have in a certain mass of N2O4, dinitrogen tetroxide. You should be able to, name that. We have 2 nitrogens and we have 4 oxygens, and it's all nonmetals, so dinitrogen tetroxide. So the first thing, and I gave you a hint, is that you have to calculate the molar mass, because otherwise we don't have a relationship between our moles and our grams. So we're given 2 things. We're given our mass of our sample, and we're given our formula. And with our formula, we can calculate our molar mass. So we want to calculate our molar mass so we can get a relationship. We also know, of course, that 1 mole equals 6.022 times 10 to 23rd. In this case, things is molecules. Earlier it was atoms. So we have to calculate our molar mass. We have our formula. We have 2 nitrogens. If we look on the periodic table, our molar mass of nitrogen is 14.007. We're going to multiply that by 2. Then we're going to add that by our oxygen, 16.00. And of course, we're multiplying that by 4. So now we have our molar mass, and that gives us our relationship of grams in 2O4 to moles in 2O4. So now we can take our grams of N2O4. We can calculate our moles of N2O4 using our molecular weight. And then using our relationship between moles and Avogadro's number, we can calculate our molecules. Remember, the term mole is just so we can comparatively look at things. Sometimes you might think moles and molecules are interchangeable, but they're not really. The molecule is the whole thing, the whole part, but the mole is just so we can compare different things. Just like a mole doesn't equal necessarily an atom. All right, so we can do this conversion starting with 76.3 grams of N2O4. Again, we have our molecular weight. We want our grams at the bottom so they cancel out. And our mole, N2O4 at the top. So grams cancel out. Now we want to convert our moles to molecules, and we have a relationship to do that. Our moles cancel out. We're left with molecules. And, of course, we started with 3 significant figures in our grams of N2O4, so our final answer should be in 3, which is all of our examples, so we don't have to worry about that. When you calculate that, you should get E. A would be what you got if you didn't use Avogadro's number and you stopped at moles. So continuing all the way through for molecules. Any questions with this one? Okay, I have some more examples to go over that are examples for what we did today in class that are set up like it would be on a quiz. And these will be on your test. Well, not these exact ones, but examples like it. So these are all things we talked about today. The first one is percent composition. We want to know percent composition, and I could ask you for aluminum, I could ask you for oxygen. In this case, I'm asking you for sulfur. And this is one I really wanted to go over, because notice we have 1 sulfur in our polyatomic ion, but we have 3 polyatomic ions. So how many sulfurs do we have total? 3. How many oxygens do we have total? 12. Because we have 3 of that polyatomic ion. So don't get confused when you're using polyatomic ions. Okay, so we want our percent composition of sulfur, and we're given our formula. So the first thing we need is our molar mass of our formula. So we could do that. We have the periodic table. So 1 molecular weight of Al2SO4 3. So aluminum, we can look on the periodic table. We have 2 of them. So 26.98 grams per mole. Sulfur, again, remember, we have 3 total sulfurs. So 3, and our sulfur is 32.07. grams per mole. That's just from the periodic table. And then oxygen, again, we have 12 total oxygen for this formula. So looking on the periodic table, of course, that's 16. So calculating that, we'll get 342.17 grams per mole. Any questions with that? It's our molecular formula. So that's our whole. That's our mass of our whole. So to calculate our percent, it's just going to be our part divided by our whole, which we just figured out, is that, times 100, because it's a percent. Percent's always times 100. So our part is not just the molecular weight of sulfur, but 3 times the molecular weight of sulfur. This is our part. Because we do have 3 sulfur atoms. And then our molecular weight is our whole. Notice our grams per mole cancel out, which makes sense because our percent doesn't have a unit. Don't forget to multiply that by 100 because it's a percent. So we get 28.12%. And I'm showing it with 4 significant figures because that's the particular periodic table I was using. That's what it gave me. Any questions with that one? Fairly straightforward. It's the same thing with this example. In this case, we're asking for percent carbon. Do you need me to go through it? The answer is so make sure you could figure that out for percent carbon. But it's the same thing we just did above. So I have 2 more examples. In 3, I want to know how many atoms of oxygen are contained in a certain amount of grams of a sample of Al2CO33. So I have my formula. I know how much I have of my pure sample, and I have my molar mass. So the question is, how many atoms of oxygen? So to figure that out, the first thing I need is to know, I have my molar mass. I need to know my relationships. And if I know my relationships, I can figure this out. So first thing, I have 1 mole oxygen equals to 16 grams oxygen. I know that. And I don't need it here. I'm not doing anything with that. But what I do know is that 1 mole Al2 CO3 is equal to 233.99 grams of Al2 I'm going a little ahead of myself with this explanation, so I didn't quite cover what I was about to say, but we have our molar mass. We can figure out our percent of aluminum, or of oxygen in Al2CO33. I was going a little ahead, something that's a little bit simpler than what I'm about to do, but this works as well. We talked about this today, that we can use our percent as a relationship. we can use that relationship saying that if we have 28.12 grams of sulfur, that's give us our relationship between our 100 grams of our full compound. So we talked about that today, so we could do that again here. So I know my molar mass, I didn't have to calculate it, it's the same as earlier. So to figure out my percent oxygen, again, my part is oxygen. And how many total oxygen atoms do I have? I have 9. 3 times 3. Don't make the mistake and say 6. It's common, but it's 9. So our part is going to be 9 times 16.00 grams per mole, which I got from the periodic table. And my whole was given to me. Times 100. So I have 61.54%. So that means my part is 61.54% of my whole, which is 100 grams. So that means that for every 61.54 grams of oxygen, I have 100 grams of my Al2CO3, which we did today. So now I have a relationship. I also know how many grams I'm starting with, which is 47.6 grams of my Al2CO3. So I want my 100 grams of my whole at the bottom. And I want my 61.5 grams of oxygen at the top, because grams Al2CO3 is only going to cancel out grams Al2CO3. So this is going to give me my grams of oxygen. But what we want is my atoms of oxygen. So we know how many grams of oxygen equals how many moles of oxygen, because we have our periodic table. So that's one relationship that we have that we can look up. And remember, I'm writing down that gram oxygen because I know that I'm not making a mistake. If I used a molecular weight for my other thing, that wouldn't work. And then lastly, we want to know our atoms, so we can use Avogadro's number. So our 1 mole oxygen at the bottom. And when we figure that out, that should come out to 1.1025 times 10 to the 24, which we can simplify to 3 significant figures, 1.10 times 10 to the 24. Remember, everything here is significant. There's a simpler method for doing this than what I just did, but we're going to learn about it on Wednesday. So this works as well. Our last one is calculating empirical formula if we're giving some percents, and that's the last thing that I'll be going over today. So here, we're finding our empirical formula, and we're assuming, based on our question, that our compound has only nitrogen and oxygen. If it doesn't have only nitrogen and oxygen, we have a little bit more to think about, but in this case it does. So our formula we're looking for is NX OY, whatever that's going to be. And remember, this could be our empirical formula. We don't know how to find our molecular formula yet. We need more information. And we're given our percentages. So our first step is to convert that to grams. And again, we're assuming that we have 100 total grams. So we have 36.86% nitrogen, so that can say we have 36.86 grams nitrogen. Now remember, what's important is that we cannot relate grams nitrogen and grams oxygen. We have to convert that to our moles. We also know how much oxygen we have. Oh, sorry, that was supposed to be in blue. So now that we know our grams, now we want to convert that to moles. Because moles we can compare. We can't compare grams because oxygen and nitrogen have a different mass. We can use our relationships from our periodic table. So starting with nitrogen, (36.86 grams nitrogen. According to our periodic table, we have 14.01 grams nitrogen for every 1 mole. So we'll put our 14.01 grams nitrogen at the bottom and 1 mole nitrogen at the top. Grams nitrogen cancel out. So what we have is 2.6310 mole of nitrogen. And that's going to be X from what I wrote at the top. We're going to do the same thing to oxygen, except it has a different molecular weight. Our molecular weight of oxygen is 16.00 grams oxygen equals 1 mole oxygen. Again, this is from the periodic table. I want grams oxygen at the bottom so they cancel out. So that gives me 3.9463 moles of oxygen. And that's my Y, or what I designated as Y as the top. So now I just plug that into X and Y to make my formula, my pseudo formula. It's not quite finished. So in 2.6310, because clearly this isn't whole numbers, and O 3.9463. So now I want to divide both of those numbers by my lowest given number, and in this case it's 2.6310. So that's going to be equal to N1, 1.5. 1.5 is too far away to round, so we're going to have to find a multiplier to give me all whole numbers. It's a 0.5, so that's a good indication we're going to multiply by 2. And you get better at doing this. You can play around with it. If you multiply by 3, you still won't have a whole number. But you can think about your fractions. 1 divided by 2 is 0.5. That's a good way to start. 1 divided by 3 is 0.33, so that's a good way to look at that. 1 divided by 4 is 0.25. 0.75, you could also multiply by 4. So we're going to multiply everything by 2, not just oxygen. That's key. It's not going to be in O3. It's going to be into O3. So don't make that mistake. And again, this is just my empirical formula. I do not know if it's my full molecular formula or not. This is just my lowest whole number ratio of nitrogens to oxygen. Anyone has any other questions?
Number 2, why is it in grams instead of percentage?
What? Oh, I'm sorry. It's, let me see. Oh, that's going to be your total grams per mole. I just wrote the wrong thing down. Actual answer is 72.07%. Your molar mass is going to be that number I just wrote down. And I have it boxed and everything. So when you're going through and you're checking that, it's going to be 72.07%. Though your molecular weight is going to be 233.302 grams per mole. That's where that number came from. I just was reading the wrong thing on my sheet. Y'all have a great day. Have a good weekend. Overall, everyone's been doing pretty well in the quizzes, so if you continue that.
Well,